Welcome to Spring LIB.
As we know, sound waves are divided into three categories: infrasound, ultrasound, and audible sound. Now, we know the harmonic position function is given by S of xt equivalent to S max cos kx minus omega t, where S max is equal to A is the amplitude or the maximum position of the element relative to equilibrium. K is equal to 2 pi by lambda is the wave number, and omega is the 2 pi by t or 2 pi nu is the angular frequency. Now, as we know that the variations in the gas pressure is delta P measured from the equilibrium values is also periodic with the same wave number and angular frequency as for the displacement, which is given by delta P is equal to delta P max sine kx minus omega t, where delta P max is equal to B S max K is equal to rho V omega S max is the pressure amplitude or the maximum change in the pressure from the equilibrium value. As we know, the power is the rate at which the piston is doing work on the element at any instant of time is given by power P is equal to F dot V. Also, we know the expression for the power, another expression for the power is delta Pi times ds upon dti. Let's expand the terms so we can write rho v omega a s square max sine square kx minus omega t. Now, as we know, the intensity of the wave I is defined as the power per unit area, which is the energy transported by the wave transfer through a unit area perpendicular to the direction of the travel of the wave. So we can write the formula for the intensity I is equal to, sorry, average power divided by A, which I can write in terms of maximum power. So delta P max square divided by 2 rho v. As we know that for the spherical wave, the intensity is given by I is equal to average power divided by 4 pi r square. Now, we should define the sound level concept. The sound level beta is convenient to use a logarithmic scale. So, it is defined as beta is equal to 10 log I by I0. So, this is the basic information that we needed for the solution of this numerical. Okay. Now, as we know, the sound of vehicle's horn changes as the vehicle moves past you. The frequency of the sound you hear as the vehicle approaches you is higher than the frequency you hear as it moves away from you. This is one example of the Doppler effect. According to the Doppler shift, for the observer moving towards source, we can write its formula V dash is equal to V plus V0 over V minus Vs times V, where V0 is the observer speed and Vs is the source speed. Also, we know that the observed wavelength lambda dash can be given by lambda minus delta lambda, but the delta lambda is equivalent to Vs over V, and as we know for shock wave, the match angle theta is given by sin theta is equal to V upon Vs. Now to do the calculation in order to evaluate the speed of the transverse wave, we use the following relation, which is V is equal to square root of T upon mu, but mu is what? The mass per length of the string, which is m by L. So as we know, the tension of the string is given by T is equal to mxg upon L. So we are going to use this one in above equation. So we will have V is equal to square root of xg. Now, in order to evaluate the velocity of the wave, we use the following relation that represents V is equal to delta x upon delta t, or dx upon dt. By rearranging the time interval, we can get dt is equal to dx upon v, but as we know, v is equal to square root of xt, so instead of that I can write dx upon square root of xt. Now integrating both the sides with limit 0 to L, we will have the time period t is equal to gx upon square root of xt. This will lead to the answer 2 times square root of L by g second. So this is the time that required.